Now, sorting takes n log n time, right? I mean, it's more subtle than that, but even if we stick with the compare and swap model, then you can do what's called select or order statistics in linear time. That's the problem of finding the element that, if the array were sorted, would be at a given position. It's the element of rank I. As it turns out, you can do that in worst case linear time on an unsorted array without any preprocessing in the compare and swap model. The super quick version goes something like this. Consider quicksort. It starts by partitioning the array on a pivot. You put everything that's smaller before everything that's larger. Now, quicksort recurses on both parts to sort them, but we are only looking for the element that's going to end up at a certain position. So wherever the border of the partition ends up, you'll know on which side to keep looking. If you take random pivots, you expect this to take linear time in total, just like you expect n log n for quicksort. But you may have noticed that I said worst case linear time, and you can actually guarantee this with a bit of a delicate procedure to quickly get a good enough pivot for the recursion to work out to be linear. Look it up if you want to, but I should say that as far as I can tell, it's not practical. Also, don't use this to find a pivot for quicksort, which, it will work in terms of big O, but it'd be an utterly grotesque way to go about it. If you actually want a particular order statistic, but not the sorted list, in practice, you should probably look up intro select. As for whose algorithm this is, I seem to remember it was Bloom, but I wasn't sure, so I looked it up, and yeah, it turns out that there's an et al. That's doing a lot of heavy lifting. It's a bit of an all-star band here. Bloom, Floyd, Pratt, Rivest, and Tarjan.